The RETH Institute is a space technology research institute funded by NASA and dedicated to the mission of developing techniques needed to establish resilient extraterrestrial habitats. With this presentation, we would like to share the motivation behind our research, explain the approach we are taking, and also define several research questions we are addressing that are contributing to the design and realization of smart and resilient space habitats that could support a long-term human presence on the Moon. We define a SmartHab as a space habitat that can autonomously sense what is going on, make decisions, and act. Our notional lunar habitat is shown here. The Moon is one of the most extreme environments that exists anywhere. It is much harsher than any environment on the Earth. We selected this harsh environment to study how to design for resilience since, strategically, the lunar surface is an excellent proving ground for habitation concepts and for learning to be more autonomous. Operating in this extreme environment will require resilience and autonomy. Similar to the NASA Moon to Mars strategy, our research aims to support a resilient, continuous, human-robotic lunar presence. Through the partnership of humans and robots, our SmartHab exists to conduct scientific activities. We are not studying how to get there. Rather, we are trying to make it possible to establish this platform to conduct groundbreaking science, such as investigating regenerative life support systems, developing power generation and distribution systems, and demonstrating surface transportation and mobility concepts. We know that this habitat will experience frequent disruptions, but we want to keep the crew safe and allow disruptions to minimally affect the time for science to occur. This may include the need to discover new knowledge about the Moon or human exposure to this environment, and many more questions that need to be answered. Consider the life cycle of our smart habitat shown in this timeline. There is an initial period of construction, and then it becomes operational. We use the notional real habitat shown previously and our day in the life schedule to put our research into context. During its life cycle, which we are considering 50 years, there are times when the habitat is dormant and there is no crew. When the crew is present, protecting them takes highest priority. The habitat's value, its mission, is the science that is produced. Because the surface of the Moon is one of the harshest environments we have encountered, thermal cycles, physical loading, radiation, moonquakes, and dust are degrading the systems of the SmartHab. While it is in operation, many types of disturbances and disruptions are affecting the habitat. Events like micrometeorite strikes and moonquakes can cause direct damage to the SmartHab and its contents. Disruptions like these are inevitable, and they have consequences that may propagate through the SmartHab and cause it to move from a safe state to a hazard state. To function as intended, a set of system operations will need to be established. Plus, the SmartHab will require routine maintenance and will need to support scientific work, while the humans go about their daily routines. Each disruption may require the use of sensors or data that are used to diagnose the damage or faults and make decisions to schedule the right sequence of repairs in order to return the habitat to normal operations. Let's look closely at what happens between a single disruption and the resulting recovery that takes place, between the red arrow and the blue arrow. When a disruption occurs, the overall performance of the SmartHab is reduced, as shown on this curve, a resilience curve. The performance will decline to some level, and then, as the problem is detected and diagnosed, repair actions can be scheduled to hopefully bring the SmartHab back to normal functionality. We aim for the design of our SmartHab to be resilient, and to appropriately use autonomy and robots to remain in, or return to, a safe state. Certain architectural features can help us get through this disruption scenario in a smart way. These are what we call our safety controls. However, during this time, when the SmartHab is not fully functional, Science is almost certainly interrupted. Let's walk through an illustrative example. Assume the SmartHab is several months into its operation and operating normally. A micrometeorite strikes. Normal operations, such as daily routines or scientific activities, are interrupted. There is a change in the regolith layer and potentially a breach in the structure, resulting in a reduction in functionality or performance. There is an additional thermal load on the system that causes the temperature inside the SmartHab to change. The thermal management system must compensate to maintain the temperature inside. And extra energy is required. So we need to determine where and how bad the damage is. In other words, we need anomaly detection and state estimation. The fault detection and health management system must sense this change in state and diagnose what is happening. This is the role of the HMS and Command and Control, C2, we are developing. And we need to decide what action must be taken to stop the decline in performance and trigger recovery to begin. Then we need to implement repairs, potentially through the actions of a robot. The habitat system must be monitored as recovery progresses until it returns to normal operations. It is important to also acknowledge that, as we move farther from the Earth, disruptions cannot be managed in the same manner that they are today. Rescue and abort become impossible. This flowchart shows the various paths that this particular disruption may take. And while this is a somewhat simplified view of just one of the 7 disruptions we are considering, it helps to put our research into context. The RETH Institute is a NASA Space Technology Research Institute that is tackling these challenges. Our goal is to facilitate the realization of resilient and autonomous space habitats. We are organized into 3 thrusts. The first thrust focuses on choosing the right architecture to support resilience. The second thrust establishes detection and diagnosis capabilities that are used for making decisions. The third thrust realizes robotic actions that will increase the ability to perform autonomous interventions. Carrying out this research requires testbeds with appropriate capabilities. To do this, we have developed 3 testbeds that are being used to demonstrate and validate our technologies and techniques. MCVT is our habitat simulator. It is a mostly physics-based system of systems model for simulating scenarios. We have built this based on several disruption scenarios. Currently, we have 7 disruptions and 18 scenarios. We follow a standard systems engineering approach for verification and validation. CDCM is our compact model, meant for rapid prototyping. It can be used for both trade studies and predictive modeling. Our cyber-physical testbed is for validation of our research outcomes under realistic uncertainties. Although they can be used for many purposes, all of these are essentially capturing our notional real habitat, and they work in concert to achieve our key objectives. Each of these tools, of course, has its own limitations, which are well documented, and we try to remain cognizant of these. Here's a photograph of the main physical component of the cyber-physical testbed. The objective here is to enable simulation of a subset of the scenarios possible in our habitat simulator with a focus on state estimation, decision-making, and robotic actions. Clearly, the presence of certain physical components will require we consider uncertainty and modeling errors in this experimental testbed. Considering the stages of the resilience curve, we have come up with numerous questions that we aim to answer through our research. We have already answered several of these questions in the past year, while we focused on building our models. We've also thought of numerous questions to be answered in future years. Now that we've explained the RETH Institute vision and what we intend to deliver to NASA, we will share some of the research questions driving the work we have accomplished this year. During nominal conditions, we have used the resilience framework to prepare for inevitable hazard events. We've also explored how to use autonomy to conduct routine operations. We have conducted research to investigate the ability to detect and diagnose damage in a hazardous state with our various disruption scenarios. To return the habitat to nominal conditions, we've researched decision-making and versatility of our habitat systems in which collaboration between human and robot agents is crucial. We've also considered the spatial and communication limitations in a space habitat and the importance of soft robotics. Lastly, we've begun to use our cyber-physical testbed to validate our techniques under various scenarios. The cyber-physical testing method allows us to more realistically simulate events and collect data. Please check out some of the other videos on this channel that address these research questions and many others. Thank you.